When 3I/ATLAs began to dim, scientists assumed it was a trick of light, dust shedding, orientation shift, maybe even fragmentation. But as data streamed in from Hubble, Webb, Chandra, and Kepler, it became impossible to ignore. This wasn't surface-level behavior. The darkening was systemic, stretching across every wavelength from optical to X-ray, and it was fast. The brightness dropped in a way that didn't match any known cometary or asteroid process. If you're still watching, subscribe now. You crave more than answers. You seek what lies beyond. Subscribe now, and be part of the few who never stop searching. Instead, something deeper was happening. Structural changes, chemical shifts, possibly even organic transformations, suggesting that 3I/ATLAs isn't just passing through our solar system, it's evolving in real time. What this means is bigger than a single object. If 3I/ATLAs is changing as it nears our sun, it implies that interstellar matter isn't static, it's reactive, volatile, and chemically alive in ways we don't yet understand. Theories now include the formation of tar-like residues, possible prebiotic compounds, and even internal collapse under thermal stress. These shifts could explain why so many similar objects go unseen, darkening themselves right out of detectability. More than just a fading light, 3I/ATLAs is showing us that the cold remnants between stars may hold the seeds of life, or the keys to rewriting what we think interstellar space really is. It was already an anomaly. An interstellar object, the third ever recorded, already glowing with an emerald light no one could explain, already throwing out signals that refused to match standard comet behavior. But now, 3I/ATLAs has done something else. Something that pushes the mystery further into uncharted territory. It's going dark. This isn't a subtle shift, it's a rapid, measurable, and deeply puzzling darkening, confirmed by no fewer than 7 major space observatories. Not just one instrument, not just one wavelength. Across the spectrum, optical, infrared, ultraviolet, even X-ray, the data all agree 3I/ATLAs is fading, fast, but not like a typical comet would. Not from dust loss, not from jetting, not from the kind of fragmentation that dims comets as they break apart and disperse. This is different. The darkening is too uniform, too synchronized. It doesn't look like surface shedding, it looks like a systemic transformation. The whole object, all at once, is changing. And no one knows why. This isn't theoretical anymore. This is observational. The Hubble Space Telescope, James Webb, Chandra, Kepler, Spitzer, every major eye on the sky with a line of sight has recorded it. The numbers match. The trend is clear. Brightness levels across multiple wavelengths are dropping in tandem. Something is happening inside 3I/ATLAs. The transformation suggests deep structural or chemical changes, not just a surface effect. Not a trick of rotation, not dust obscuring light. This is a shift in the object's physical state. The way it absorbs, reflects, and emits light is changing, across the whole body. That kind of behavior doesn't fit any existing model of cometary or asteroid evolution. It forces a reassessment of what interstellar objects actually are. Until now, the assumption has been simple. Interstellar bodies are inert, ancient, cold relics flung from distant systems, frozen solid, chemically neutral, and geologically dead, fossils drifting through the void. But 3I/ATLAs is telling a different story. It's not inert, it's not static, it's not behaving like something passive, it's evolving. And that word changes everything. Because if interstellar objects can evolve, if they can undergo transformations during their brief pass through stellar systems, then the models that treat them as dead rocks no longer apply. That means interstellar debris might not be lifeless at all. It might be dynamic, reactive, chemically alive in a sense. And if that's true, then every assumption about the chemical quietness of the deep cosmos needs to be revisited. One of the leading theories behind the darkening involves complex organics, tar-like materials, prebiotic residues, the kind of compounds that form when radiation hits carbon-based molecules over millions of years in cold, dense space. These materials are known to darken when exposed to heat and light, and 3I/ATLAs is now deep inside the sun's influence. That theory fits, but it's not complete, because the rate of change still defies expectation. The dimming is happening faster than would be expected from passive surface reactions. That points to something deeper, possibly subsurface chemistry, structural collapse, or even phase transitions inside the object. Internal chemistry, understellar radiation, acting faster than models allow. If this is a layer of organic matter transforming under heat, thickening, reacting, darkening, it could be one of the clearest signs that interstellar bodies are chemically active, and not just active, but capable of complex reactions that resemble the early steps toward biology. We're not talking about life. Not directly, but prebiotic chemistry. That's now a serious possibility. Because if 3I/ATLAs carries the raw materials for life, carbon chains, complex molecules, radiation-processed compounds, then it represents more than a scientific curiosity. It becomes a vehicle, a natural carrier of the building blocks for life, drifting across star systems. This darkening isn't just a mystery, it's a potential signal. A signal that matter in deep space doesn't just freeze and die, it processes, it transforms, it carries potential. That raises more questions. How many other interstellar objects have passed through the solar system undetected? If these bodies are prone to dimming, becoming darker and harder to spot as they enter systems, then it's likely we're missing most of them. Detection methods rely on reflectivity, on light. But if objects like 3I/ATLAs are chemically darkening in response to solar energy, then we're blind to a whole population of interstellar visitors. The implication is clear. Our view of the galaxy is limited, not by instruments, but by the behavior of the objects themselves. They change in ways we didn't predict, and that changes the numbers. It also affects our understanding of their structure. The darkening may suggest a thermodynamic process, something happening beneath the surface. Not disintegration, but collapse, compression, a drop in porosity. Maybe a chemical phase change triggered by heat. Maybe a realignment of internal materials. None of that fits traditional asteroid behavior. It's a transformation that looks closer to geology or chemistry than simple melting or erosion. That level of complexity forces a cross-disciplinary response. Astrophysicists are involved, chemists, planetary scientists, astrobiologists. The phenomenon demands integrated models, ones that can handle radiation damage, thermal stress, complex molecule formation, and physical restructuring, all at once. And it's all happening in real time. This isn't a historical analysis of a fossil rock. This is a live event. A change being recorded across the spectrum. A darkening comet that might be rewriting what we think interstellar debris even is. The implications reach beyond science. Because if the building blocks of life can travel this way, if they can survive interstellar journeys, react under stellar conditions, and evolve chemically, then the process of planetary seeding becomes less hypothetical and more probable. Life, in its earliest stages, might not need Earth-like conditions to begin. It might start inside objects like 3I/ATLAs, cold, silent, drifting, until heat and light activate something. The darkening could be decay, or it could be development. Either way, it changes the frame. And it reminds us how little we know, how narrow our assumptions have been, how much complexity might be passing through our solar system, unnoticed, unmeasured, undocumented. Not anymore. Not with instruments like Webb and Hubble and Chandra focused and recording. Not with infrared, ultraviolet, and X-ray eyes tracking every movement. Not with global networks alert and coordinated. That level of cooperation matters. This isn't one agency. This is science at scale. Space-based telescopes, ground-based observatories, international teams racing against time to gather data before 3I/ATLAs fades from reach. Because that's the other truth. This is temporary. Soon, the object will be gone, fading into the outer dark, its light dimmed, its secrets buried in shadow once more. What we collect now is all we get. And what we've collected so far already breaks the model. The darkening isn't the end of the mystery, it's the start of something bigger. A challenge to current models. A signal to rethink interstellar chemistry. A warning that the cosmos is more reactive than we thought. And a quiet question hanging over it all. What else have we missed? Like, share, subscribe. This is only the beginning. 3I/ATLAs is disappearing before our eyes. But it's not vanishing into the void, it's undergoing a transformation we don't fully understand. That alone makes it a landmark event in modern astronomy. Because this wasn't supposed to happen. The behavior we're seeing wasn't predicted by any model, and no one, absolutely no one, anticipated an interstellar object would darken so rapidly, so completely, across every spectrum. And yet, that's exactly what's happening. This isn't dimming from distance. It's not an orientation shift. It's not shadow. It's not spin. The transformation is intrinsic, internal, real. When you observe an object like this, one that doesn't belong here, one that's just passing through from the distant reaches between stars, you expect a kind of passive decay. Ice sublimates, gases vent, surfaces erode. But none of that explains the synchronized drop in brightness being observed by multiple space telescopes across optical, infrared, ultraviolet, and even X-ray. The evidence points to something more fundamental: a phase transition, a chemical shift, a structural change. And what that tells us is simple and uncomfortable. Interstellar objects are not what we thought. They're not inert. They're not geologically frozen relics. They're not finished. They evolve. And 3I/ATL is the first time we're watching that process happen live. This is more than an academic development. It changes how we think about the material that flows through our galaxy. It forces us to acknowledge that deep space may not be as chemically quiet or structurally stable as once believed. Because if this object can change in transit, if it can respond to radiation, to heat, to solar proximity, then so can others. Which means the models that treat interstellar debris as chemically neutral, biologically irrelevant background material, they're obsolete. And the consequences are staggering. One theory gaining traction among planetary scientists involves the formation of complex organic coatings, carbon-rich, tar-like residues, that emerge when solar radiation interacts with volatile rich compounds. These substances don't just form passively. They react. They harden. They change how an object reflects light. And more importantly, they might carry prebiotic significance. Because these aren't just carbon molecules, they're processed, altered, activated. Some may contain amino acid precursors. Some may act as cosmic polymers. And when they undergo chemical evolution on contact with heat or ultraviolet radiation, they become more than inert matter. They become chemical candidates for the origins of life. If this is what's happening on 3I/ATLAs, if this darkening is the result of organic surface chemistry, then this is no longer just a physics story, it becomes a biological one. And that puts 3I/ATLAd in a different category. Not just an object of interest. A test case. A window into chemical pathways that predate life itself. That possibility reshapes our understanding of how life begins. Because for decades, theories about panspermia and the interstellar transport of organics have been debated without clear observational support. Now, we may be watching it unfold in real time. And that's why scientists from multiple disciplines are now involved. Astrophysicists aren't working alone. Organic chemists, spectroscopists, astrobiologists, thermal modelers. Every corner of space science has something to say about 3I/ATLA, and all of them are saying the same thing. This isn't normal. The rapidity of the change, the consistency across wavelength bands, the lack of fragmentation or jetting, it all points to a transformation deeper than surface erosion. One explanation centers around porosity. If 3I/ATLA as a highly porous internal structure, like a sponge of cosmic dust and ice, then heat could cause internal collapse. Cavities close. Materials compact. And as voids disappear, reflectivity drops. That could explain part of the darkening, but not all of it. Because collapse alone doesn't account for the chemical shifts being detected. Spectral readings are beginning to show new absorption features. Weak but persistent. Possibly signs of new molecules forming. That means chemistry is not only changing the structure of the object, it's rewriting its composition, and that opens another question. What if interstellar objects are chemically activated by proximity to stars? What if this is a process, not a failure? It's possible we're watching the early stages of a catalytic event. One that begins only when the object enters a star system and is exposed to elevated radiation levels. A kind of awakening. It wouldn't be biological, not in the way we define it, but it would still be evolution, molecular, structural, transformative. And if that's happening to 3I/ATLAs, then we have to consider the possibility that these events are common but invisible. Because what do darkened low-albedo objects look like after transformation? They look like empty space. They stop reflecting. They fall below detection thresholds. They become stealth. That means 3I/ATLAd could be just one of many. The only difference: we caught this one before it finished disappearing. The observational bias is real. We build detection systems based on light. But if light is temporary, if it fades rapidly under solar conditions, then our entire catalog of interstellar visitors is incomplete. We're seeing only the brightest, and only the earliest. The rest are fading ghosts. Missed, misclassified, or never seen at all. Which leads to a staggering realization: we may be surrounded by more interstellar material than we thought. Chemically rich, structurally dynamic, possibly seeding systems as they pass through, and we're only now learning how to see it. But to do that, we need better systems. More than telescopes. We need multi-spectrum arrays. We need dedicated probes. We need rapid response missions that can launch within weeks, not years. Because when objects like 3I/ATLAd enter our system, they don't stay long. They pass through quickly. And when they change, they don't wait for us to figure it out. This event has made that brutally clear. The coordinated effort from Hubble, Webb, Chandra, Kepler, Spitzer, it's a model for how we move forward. The future of interstellar object science isn't passive observation, it's rapid, integrated, multi-instrument deployment. Ground-based and orbital, infrared, UV, X-ray, radar. All focused, all immediate. Because the universe doesn't operate on our schedule. And sometimes the biggest breakthroughs come disguised as anomalies. Like a comet that glows green, and then starts to vanish. And now, beyond the science, comes the part that's harder to quantify. The philosophical impact. Because when an object like 3I/ATLAd challenges everything we thought we knew, when it refuses to behave, refuses to obey the rules, we're left with more than unanswered questions. We're left with awe. We're reminded how limited our understanding is, how narrow our models still are, how young we are in the process of understanding a cosmos that clearly doesn't need our permission to surprise us. The rapid darkening of this interstellar visitor forces us to stare straight into the face of complexity we weren't prepared for. And that kind of confrontation is important. It's what drives science forward. It's what forces humility. And it's what keeps the door open to the questions that really matter. What else is out there? How much have we missed? And what's waiting in the dark? Waiting to be seen, even as it fades. 3I/ATLAd isn't just data. It's a message. One we're only just learning how to interpret. 3I/ATLAd isn't just slipping away. It's changing the field as it leaves. Every frame captured, every spectral band recorded, every photon measured across 7 major observatories is telling us the same thing. What we thought was dead was never dead at all. It's been easy, too easy, to think of interstellar objects as fossils, as frozen leftovers from planetary systems that came and went billions of years ago, carried here by nothing more than inertia and time. But that idea doesn't hold anymore. Not after this. 3I/ATLAd has rewritten that script in real time. Its rapid darkening doesn't just challenge the idea of inert space debris. It erases it. This object didn't just passively fade under sunlight. It responded. It reacted. It evolved. And here's what that really means. The building blocks of matter drifting between stars aren't static. They're reactive. They're volatile in the best sense. They carry memory, chemistry, complexity. They hold the fingerprints of other worlds, other stars, other histories. And when they get close enough, when the heat and light hit, they change. Not slowly. Not imperceptibly, but visibly, measurably, urgently. The silence of deep space was never lifeless. It was waiting for the right conditions to speak. And now, under our eyes, it's speaking. This wasn't a high-speed flyby. It was a transformation, and we were just lucky enough to be looking. So where does that leave us? With a new class of objects. Not asteroids. Not comets. Not dead rock. But evolving interstellar matter, complex, chemical, alive in the way only non-biological systems can be. They enter systems. They react. They transform. They vanish. And now we know that's not rare. It's likely common. We just haven't had the sensitivity to catch it before. Or we weren't watching at the right time. But with 3I/ATLID, we were. And what we caught forces us to look differently at everything else. It's not just about this one object. It's about what it reveals. That space is not static. That interstellar debris is not just passing through, it's participating. Participating in chemistry, in evolution, in possibility. And when something like 3I/ATLID dims, not from destruction, but from transformation, we are watching the galaxy breathe. One object, one transit, one fading light, and 1,000 new questions. What comes next isn't up to the object. It's up to us, to respond, to prepare, to listen, because the next one will come. And when it does, we'll know better. We'll be ready to see what we missed the first time. Like, share, subscribe. Because what looked like darkness was a signal all along.